today's webinar is going to be around the TimeNode economics. So you get a small introduction on the last webinar. We're going to discuss a little bit more. Today, I'm gonna be joined by my teammate Logan. So, Logan, say hi to the community.
Hi guys, Logan here. Thanks a lot for making it out tonight. Really excited to have this webinar with you all.
Yeah, and my name is Piotr. If you don't recognize my voice, yeah, let's start. I guess we just go with a short roundup of the what's going on, what we're working on, and all that stuff. Some status updates. Yeah, all of us, and all of you, and we keep still waiting for the for some concrete summary on the contract audits that we're waiting for from the Zero Knowledge Lab. So uh, there is a slight delay, but we hopefully get this soon. So yeah, as you may know, we working on a 2 weeks batches or the sprints, and last week we presented you what was included in the last release. Now the next release is scheduled at the end of this week, Friday. And basically we've been working and we've been focused, the team has been focused on time node stability and security. So we're planning to bring you new exciting stuff around the time node. We are not gonna spoil that yet. You might I don't know if that's somehow available on GitHub or but stay tuned. We're working on something cool. More updates coming up later. Obviously, besides these new features, it's always some bug fixes, new improvements. We make sure that everything runs smooth and doesn't break and all that stuff. So that's really the priority for us at the moment and during the past 2 weeks. Um, yeah, obviously, besides tons of research, tons of discussions, tons of brainstorming, and this is like a bread and butter for our team currently. Yeah, so that's something that I was working with the other teammates. So the economic model, you can find this, on GitHub. The link is here. So basically, this webinar is going to, in like, describe the concept on how we build that, what does it mean, and all that stuff. The full article is available under this link. So if you have a little bit more time, you wanna, read that stuff, um, just go there and read. Let us know what you think. As I said, it's just a one of so it's a proposal. It's the model that obviously is not like 100% accurate or includes all the possible cases, edge cases, and all that stuff. It's here to kind of help the estimation easier, so we understand a little bit more, what are the things that influence the economics, um, yeah, etc. So this
Y-
is really important.
Yep. If you guys are interested in at all about the economics of the Ethereum alarm clock, I highly recommend you read this paper. Piotr did a really great job in really capturing all of the parameters and all of the moving pieces that come into a complex system like the alarm clock. And it's a good read. But I do want to just make it clear to everyone that this economic model that we'll be talking about here is for the Ethereum alarm clock, and the economic model for Chronos will be a little bit different, but we'll go into that more deeply through the rest of the webinar.
Yeah, exactly. So this is about the Ethereum alarm clock. This is something that we're waiting for the audit. It's going to be live soon, um, and most of the work is already done, and we're looking into this as a base on how we can improve in the next next thing in the Chronos, how we can improve, what's really the problems here and all that stuff. So if we obviously have been working on Ethereum alarm clock for months now. We learn a lot of things. We know better, the problem that we're working on, etc. So this is something that we wanted also put into the community, the whole community, to see the reaction and get some feedback, etc. So hopefully everyone's going to enjoy that. So yeah, okay, let's sit tight. We're going into what I was working on past 2 weeks. Hopefully, it's not gonna be too boring. I will try to basically go through this smoothly and don't really, bring all that stuff that is in that paper that you can find under the link. I see the link is also now into someone posted in the question box. So this is cool. Thank you. All right. So economic model. Basically, we have what I put is like we have 3 different cases. So the optimistic path, which is that the time node is successfully claimed and then executed the transaction. So this is expected payout in that case. Now, so the explanations, right? The PMOD is a payment modifier. So this is a part of mechanism that works very simple in a way that during the claiming window, the payment modifier is 0 at the beginning of the claiming window, and it is 1 at the end of the claiming window. Claiming window is happening before the execution window. So execution window starts when you or someone else trying to execute that transaction. It puts the start of this window into the smart contract, and the smart contract is also calculating the claiming window, which is happening before. So how this payment modifier works, it basically the later time node is trying to get the transaction for, claim the transaction, the higher the payment will be. So it is a modifier that is, multiplied by the time bounty. So for instance, giving the time bounty like 1 ETH, if the payment modifier is 0 because someone claimed that this is 0, in the first block, it's gonna get like no bounty, or maybe I don't know, yeah, something like this. And if it claims at the end of the claiming window, it's gonna get the full time bounty. You might question, why? Why is that? Why basically is that happening? Is the original idea from Piper that we, this Ethereum alarm clock has to deal with a problem of what I call swarming, which is that basically the time nodes are incentivized to execute the transaction or interact with the blockchain at the one point in time, because there's someone who's going to execute first, get the time bounty, right? So everyone is incentivized to execute as soon as possible, which actually leads to a collisions, meaning that only one out of n is going to get this time bounty successfully. And this is how it is actually represented here. So do you see my mouse pointer? Can you give me like 2 into question box? I'm not sure about that.
I can see it.
All right, so everyone else, I guess, as well. So yeah, so this is n number of nodes, which is like, number of time nodes that are competing for the execution. So because basically you can, in the situation that you have n time nodes, so and everyone have the same exact chance to get this transaction, executed, then if that's the same chance that basically 1 by n you will get the transaction, and every other else you will probably take the cost of the failing transaction because someone else, was before you. So that's kind of the raw idea. What we did, and we kind of introduced some mitigation mechanism that is here denoted as AX, which means that there is some probability that you won't pay this failing transaction cost. Hopefully that makes sense. Logan, so can you from the implementation point of view, could you explain what we've done in order to kind of keep those time nodes not sending the same transaction if the other transaction exists on the blockchain?
Yeah. So we've talked about this problem quite a bit over the webinars and during our presentations as well. So it's the issue of swarming or transaction collision. Um, and so this mechanism that we're using that's represented in this equation here as AX. So this is the check the time node performs before sending a transaction, and it checks for the the transaction pool to see if there's any other transactions going to the contract. And if it sees another transaction, it'll simply just not send a transaction. It'll know that if it sends a transaction, it'll cause one of these collisions, which would lead to a cost onto the network. And so it simply just holds back and doesn't send the transaction. Um, I've talked about in the past how this is not the best solution because it's implemented in the TimeNode uh, logic versus into the protocol on a contract level. So one thing that we've kind of always have thought about is what if someone comes along and wants to write their own custom TimeNode uh, client, and we think they should be allowed to do this if they want to, um, but they could basically forego this check and start causing some transactions to start failing. Uh, it might be on purpose, it might be on accident, but essentially that's our safeguard there that we've put into the time nodes. And yeah, that's A of X.
Yep. Um, yeah, so you might ask why actually we can't mitigate the whole thing completely. And because, we can't really, because the only way would be to kind of have every single time node be connected to the same the same node, to the same Ethereum node, as well as every person who is going to schedule the transaction also should use the same node. Then actually there is one pool visible for all the time nodes, and then they can quite easily then identicate, right? If your time nodes using the other providers or using the full nodes that you are hosting, then actually there is always some time for the synchronization of those mempools. So whatever the transaction is being broadcast via the one node, it needs some time to be broadcasted over the other nodes. And that's why basically, even though there is this mempool check available, it might actually lead sometimes into some problems. And you will see how we put some numbers, for the simulation. I use something like probably like 95% of accuracy, which means that 5% of times it might actually cause you the cost. So making the whole simulation slightly more realistic, etc. So yeah, but you will see that later. All right, so the second part, actually the second thing is that payout after successful claiming and missed execution. So we have this deposit thing in the protocol, which means that if you are claiming the transaction and the deposit is required, then you need to send and lock the deposit into the smart contract. But if you actually lose if you lose, or if you don't want, if you don't execute the transaction at given time, given period of time, then actually you are going to lose this deposit. So this is the expected payout. So you will pay the claiming cost, and also you will pay so you lose deposit, so minus deposit. Now here we have the other chance, because again, when we continue about the deposits, then when you or any other node is going to lose the deposit, then or not execute, then this deposit is available for any other time nodes for free-for-all execution, which means that the free-for-all execution will end up with TimeBounty plus deposit thing minus obviously minus the chance for the collision, so the expected payout if the collision happens. So that's basically these three components, and then I also put something like the probability, so some sort of variable that is going to say or model the way, how much often are you going to lose this deposit. Obviously, in the worst case, you are going to do this always. In the best case, never, right? So I will show you later, but I used something like 1% of chance of losing the deposit and something like that. So bear in mind that these are some numbers that we pick together with the team, more based on the intuition. We don't have, I mean, we are running our time nodes, we are observing and monitoring that. But still, we still don't have this, kind of real numbers where we can, learn when we go to the mainnet. Hopefully, it's going to be low and it's going to provide, um, just doesn't provide into the problems where people are losing the deposits or making the time nodes not profitable to run. So basically here is that 1 minus probability of losing deposit. So this is your modifier for the first part, which is like the successful execution, plus you have some chance that someone else is going to lose the deposit as well as you lose the deposit. So this losing deposit probability is equal in this equation for you and for any other node. Obviously, if you are going to uh, have better accuracy or reliability of running your time nodes, and let's say the rest of the network is going to lose the deposit more often than you, then actually this is in general better for you as a participant of this network. So in general, any advantage that you have on reliability and the running cost is always going to increase your total payout of running the time node. Yeah, and then basically we get, as I said, we get some, I get running some simulations. If you go to the link that has been distributed already, you will find the source code that you can take and run basically, and skip basically experiment with that, because these numbers again are by taken by intuition. So here is some trivial simulation on the model, and that assumes that we are going to have something like 8 time nodes. All these numbers, by the way, for the simulation are the mean values in the normal distribution, which means that, and I'm using the Monte Carlo simulation thing, which means that we're doing 10,000 iterations over the distribution around this mean number. So what does it mean? It means that, makes this thing a little bit more realistic, meaning that the time, like the number of time nodes is not always gonna be 8, but it's gonna be like 6, 9, 10, around the 8. The frequency of having 8 time nodes is gonna be the highest, and then based on the normal distribution, we have different numbers. Same for the time bounty, deposit, and all these other parameters. And we get into these numbers, and basically one of the assumptions was that where is the profitability threshold. So from what point in time or how many transactions has to be executed by the time node to make it basically profitable, right? So I set this target for roughly 7 USD monthly, because basically this is this is the value that we take from our hosting Heroku thing, where we actually keeping our time nodes, and it's basically 7 USD monthly. So I took this as a baseline. So that's how much does it cost us to run 24/7 one time node. So it's 7 USD. Which if you use some calculation, and I at the point when I was creating this, if there was something like 700 USD, then you will get that this is more or less 1 million of gas. So the reason I'm using the gas as a common thing is that it's not really it's constant. It's not related with a gas price of the Ethereum network, as well as it's not denominated to USDs, because that's constantly changing. So this is, I think, the most stable thing, because the transaction is, or the deposit or whatever TimeBounty will, if we assume this in gas, it's gonna be constant. It's obviously gonna be different in when you translate this to Ether or in to USDs. So most of the people probably will calculate this into the USDs. Nevertheless, so this table is a result from so this is like a payment. So what does it mean? So the payment modifier for this simulation is an input. So it went from 0 to 1, right? So from the beginning of the claiming window to the end of the claiming window, and I just remove the payment modifiers that's going to yield the non-profit. So if you are going constantly claim the transactions before before it's actually profitable for you, then you will keep losing all time, right? So from modifier 0.7 towards 1, it is basically profitable. The only difference is since the margin, the profit margin is lower, if you claim earlier, then basically in total you need to claim and execute successfully much more of the transactions. So in the best case, if you are able to get at the last of the block, then you need like roughly 100 transactions monthly to cover the cost of 7 USDs for running the TimeNode. Obviously, given all this price and Ether price to USD and other conditions which are constantly changing. In the worst case, you need to execute like 700 transactions monthly, scheduled transactions, which means given the let's say 8 time nodes, and everyone have pretty much similar chance to get those transactions, it means that availability for those transactions in total has to be like, let's say, roughly 10 times more, so 7K transactions monthly, which is not huge. I guess something like we have currently on the Ethereum network is like 80K daily. So you can see how basically where we are, and obviously assuming something like 1% of the total Ethereum transactions going to be through the scheduling, it is going to yield like 8K, 800, sorry, 800 transactions like daily. So monthly, much more. So we have a question from Brendan. How would this translate into standard figure? Example, could we use an average time node size for projections? I'm not entirely sure what do you mean by average time node size. Could you specify this a little bit more? We can just go back. Dollar figure. Yeah. So basically, in the Ethereum alarm clock, all the time nodes are considered, equal. So basically, the running cost is whatever you can have. Meaning that if you want to use like Heroku, it's like $7 monthly. If you want to use this, if you want to run your time node on your PC while you're working, then probably you don't consider this as an extra cost. It's gonna, if you keep your PC open, then your cost is like probably around zero, right? So which means that if you get like couple of the transactions claimed and executed, then you are already profitable. So this is the case when you 24/7 online and all that stuff. Hope that answer your question. Yep. So here actually there is a couple. Let me check. Yeah. So here are a couple of the graphs that are actually taken from the simulation. So here is actually the payout per transaction versus the network. So the amount of time nodes. And here actually, since you are competing against the other time nodes, and if we put the assumption that everyone is going to have the equal chance, then basically the payout is going to be smaller if we have more time nodes available, right? On the other hand, there will be no more time nodes available on the network if that's not profitable. So what I'm saying is that we are going to probably observe the equilibrium between the amount of time nodes, time bounty, and basically the payout per transaction. Where it's actually going to end up, we don't know. It's going to be probably moving. Logan is going to talk to you. Going to present this a little bit, yeah, a little bit later on this live stream. He's going to talk about the competitive markets and how they work, and in general why we think Ethereum alarm clock or the time node market is a close thing to the competitive market. So it's going to be explained a little bit later. Another thing is that obviously, so that what makes us actually thinking about the improvements for the scheduling protocols is that the claiming cost, which is something that we as developers try to make as low as possible. So that depends on the smart contracts implementation, is actually obviously negatively influencing the payout, because
Baby,
if
baby, he got scared. Look, baby, stop. Can you stop it? Look, he peed all over the.
sorry for that, guys, I know.
Sorry for the interruption, guys.
Yep. Um, yeah, so we have the payout per transaction, which is relatively to the claiming cost, and the lower claiming cost, the higher the payout. So you can see that here. Here we have so the payout is going to basically zero when the claiming cost is over some amount. So that basically gives us the need for execution, for bringing the better and more scalable and more optimized implementation. Yep. So here actually, I think last slide I probably put everyone to sleep. Sorry for that. It's try to get this up and running. So what we call it is whoops. What we call it is a Chronos case, which means that Chronos is the next generation protocol. We're looking into the other way of implementing the claiming mechanism, off-chain claiming, or some variation of the something like the on-chain claiming. Basically, here we have the assumption that the accuracy of this mechanism of the collision is 1, which means that actually when we implement this off chain, that there is no cost for running for this. Also, the claiming cost is 0 gas, which means that this actually is it's the claiming is off chain, so it doesn't really put any extra gas cost. And having these assumptions and everything else virtually the same as in previous example, we basically using this model, we see that well, the payout for this payment modifier is like roughly 3 times higher, which means that you can see and feel like what's the how much cost and effectiveness is the claiming, or basically in general the cost of transactions on Ethereum employs. So this is something that we use as a kind of and the idea, and and it's what we expect. Obviously, this improvement might be different, but we definitely is going to see definitely some improvements in that regard. Okay, let's jump into the competitive market. So, Logan, the
Yeah.
mic is yours.
Thank you. So competitive markets. So as we're doing these analysis over the time node economics, we're trying to basically figure out what the key components are so that we can engineer a more profitable time node. Uh, Engineer a protocol that would incentivize people to run time nodes. So I'm going to talk a little bit about what a competitive market is, how this applies to the Ethereum alarm clock, and what we're doing in Chronos that we're trying to make a little bit different. And like always, this is stuff that we're currently developing, and it's a lot of it is still research phase. So just keep that in mind as I'm going through it. Next slide, please. So in a competitive market, there's this idea of the perfect competition, which is also known as the point of equilibrium in a market. So this is when it's the opposite of a monopoly. So it's when there's plenty of actors to assume both the demand and supply side of a market. We can apply this to the alarm clock time node market because the time nodes are pretty the barriers to there's basically no barriers to run a time node. You just kind of download the source code or go to the DApp and unlock your wallet and you're running a time node. And there's no barriers to the supply of the scheduled transactions either. It's a completely open market. So we see that the prices will reflect the real supply and demand. So in this case, we're the screen share is on. Piotr. So in this case, we can view the supply as the scheduled transactions in the Ethereum alarm clock market, and the demand to be the time nodes that are executing the transactions. So here's just the classic supply and demand curve. As there's more supply, the time nodes, there'll be more demand for time nodes, and this will. So if we look at where the red line meets the blue line, we have the equilibrium point, and as the blue line continues to go up from Q1 to Q2, you see that the first demand line D1 goes down. So what will happen is that more time nodes will see that there's an increase in supply and join the network because they see they can make a profit, and will push the market closer to the equilibrium point and create the new demand curve at D2 and the new equilibrium point at P2 Q2. So this is essentially the idea behind a perfect competition market. And next slide, please. And so we think the Ethereum alarm clock time node market will turn into something like this, where the long-term effects will be that the time nodes will reach equilibrium with the amount of scheduled transactions. So the number that we were using before for the cost of running a time node, which was $7. This is the cost of running a Heroku instance 24/7 for 1 month. And so you can think about the kind of minimum value that needs to be transacting in the Ethereum alarm clock system as that price, as $7, because you need to incentivize at least one time node to be running. And you can kind of roughly guess that for each iteration or each step of $7, you'll see roughly another time node in the network. If all of the time nodes act rationally and aim to maximize their profits, as well as all the schedulers act rationally and try to minimize their costs. This is basically what will happen, where the time nodes will always increase to reach to fill the demand side of the supply. So essentially what this means is that the long-term effects is that time nodes will turn out to be profitable in the short run and minimally profitable, trending toward zero profit in the long run. And this is not necessarily a bad thing. This is usually something that is desired in a market, and especially something that is a utility like the Ethereum alarm clock. It might actually be not a bad thing at all, but Chronos might have a slightly different mechanism, and this is due to the claiming mechanism that we're using. So the alarm clock looks a lot like a perfect competitive market because there's no barriers to entry for the time nodes. So if there's $7 of bounties in the system over 1 month on average, there will be one time node in the system on average. If there's $14, there will be two time nodes. And if the system only has $7 of volume the next month, then one time node will be making less money and will likely turn off, and only one time node will be running because only one time node will be profitable. In Chronos, when a time node joins the claiming pool, it actually is signing on to something that creates a little bit more friction in being able to enter and exit than just logging into the DApp or turning on the command line. So we're not exactly sure how this will affect the economic side of it yet, but there'll be a different economic model for sure, depending on the final claiming mechanism we use in Chronos. And just in case anybody doesn't know, we're considering some kind of proof of stake system where time nodes would stake the day token and be either assigned or randomly selected to execute transactions in proportion to how much day they've staked. And then we have like a slashing mechanism to ensure that these transactions get executed. So that's basically my I think that's my last slide.
Yeah, thank you. That was pretty exciting. Um, yeah, again, so since while we don't have any exact numbers of how it's gonna be, about the model in Chronos, because it's definitely too early for that. But one thing that we are pretty sure is that it's gonna be definitely, on the lower costs, which means that it's gonna be more profitable in the long run. One of the things that definitely is going to change is that we don't. I mean, like today in the Ethereum alarm clock, the claiming cost is always per transaction, which in the long run is quite a significant cost. While in the Chronos, it's gonna be changed, so it's gonna be one-time action, or definitely not that often as per transaction. So that's gonna be definitely an improvement in that regard. Um, all right, so let's start wrapping up a little bit. Yeah, I guess at the end we just small status thing. So that's pretty much of what we're working on and where we are. We have the claiming, and this is like partially research and proof of concept. We have cool stuff on our GitHub, the priority queue, that is one of the possible implementations. Also, the conditional scheduling, that was a topic for the previous webinar. So if you're interested in hearing about that more, you can find the previous webinar and listen to. Confidential transactions or confidential scheduling is still in the research department, and we definitely this is really important and exciting feature that we at some point planning to bring. It's definitely tough and have a lot of issues with the current state of the network tooling and in general zk snarks. Yeah, the last thing is the IPFS/stateless implementation proof of concept available on our GitHub. You can check what we have and how we improve on the scheduling protocol. So yeah, these are the links that you want to follow to. Our page, blog, we pushing quite a lot of content pretty recently. All our GitHub accounts, check them out. Join the Telegram channels to chat with us, or the Gitter channels if you more developer focused and you prefer that. So let's take a look at the question box. Do we have any questions to answer? I see. Okay, one question. Any idea on amount of stake needed? So, yeah, I don't know. Logan, do you want to answer this question?
Yeah, I guess I can take a stab at it. So right now there's no minimum amount of stake that we're requiring. There probably will be before the whole claiming mechanism is finalized. I'm not totally sure what that number will be, but it'll have to be something that is large enough to ensure that that when it's slashed, that it's enough value to slash from the time node, that the time node uh, won't misbehave and uh, act